The Bohr model. Now we have the idea of quantization without a clear understanding of why yet, but quantization, photoelectric effect, the Balmer's line series, right, the Rydberg line series, the photoelectric effect. Now, Bohr came along and started applying this now to the hydrogen atom. See, classically speaking, the hydrogen atom, or any atom, was kind of seen as following what they call the planetary model, mimicked after the planets circling around the sun, and which is a very macroscopic condition, of course, but down in the microscopic, maybe not so much true, right? But again, classically, we weren't aware that there was a difference yet, and so they have the idea of this nucleus right in the middle, and the electrons which are revolving around the nucleus, very much like a planetary system, the planetary model. Right, there it is, the nucleus with its protons and its neutrons. The electrons whip it around here. Okay. Now this is the wrong picture. This is not what an atom looks like at all. Yeah, the nucleus is in the middle and the electrons are out there, but they're not revolving around like planets around the sun by any means. In fact, they don't even look like planets, we're going to find out. Just the wrong model. Okay, and Niels Bohr started to pick out, or maybe chip away at that wrong planetary model a little bit, right? And he came up with what we now call the Bohr model, and technically it's for hydrogen atoms or hydrogen-like atoms only. You can't just apply it to any old atom. But again, it's a first stepping stone to understanding what atoms really do look like. So 1913, Niels Bohr, first of all, he said, hey, why do we have to keep this planetary model? Let's come up with something new, because we already see that things are breaking down in the microscopic. It's not really working quite like we think. And so he was adventurous. He decided, let's go with a totally different model. He said, hey, instead of electrons being like planets going around the sun, we're going to say that they are in some of what they called stationary type states. They're not moving around. He said he didn't really know what they looked like, perhaps, right? But they're not moving around and around. They're kind of locked into these stationary states, right? Maybe involve spinning around. I don't know what. I really don't know where he was going necessarily with it, but he realized that the simple model wasn't going to work. So he said they're locked into some stationary states, and the important thing was each different type of stationary state would have a certain amount of energy. Right? So one of the problems with the planetary model, except for, I mean, other than that it's just totally wrong, but if they were like planets going around the sun, a changing pathway as you go around, that's a change in direction of the vector, which implies there's a force being applied, which also means there's some type of an energy exchange. But a resting atom doesn't show an energy exchange by any means like that. And so that alone shows that it can't quite be like that. Okay. But anyway, planetary model, not good. And so again, let's move to a stationary state sort of a model, the Bohr model, where whatever they look like, right, I could take an electron in one state, whatever it looks like, and put it into a different state or a different state, and each one of these different states had a certain amount of energy. Now these states had to be such where they were stable somehow. You know, the electron didn't just plow into the nucleus or whatever, right? But there are different stationary states, and we'll see about these stationary states when we talk about waves and invoking wave natures of electrons in an upcoming section here real soon. Okay. Number two, he decided that, hey, when you emit or absorb energy, kind of like, hey, when we take that hydrogen gas and we shoot the electricity through it and it releases these photons, and we saw the line spectrum of the different types of photons it released, right? He said when it's releasing the energy for those different lines of light, what we're doing is we're moving from one state to another, maybe from a high energy state to a lower energy state. Well, where does that energy go? It goes and is released as that photon. And because the states are always, they're stationary states, so they're kind of locked in as far as the amount of energy that they can have, as you drop from, say, maybe an energy of 10 down to an energy of 7, hey, you're releasing 3 chunks of energy, and that energy is being released as the photon, which is light, and we see, hey, a purple line or a yellow line or something like that. Okay, so which kind of implies, hey, if this is true, then those 4 different lines for hydrogen that we see in the line spectrum correspond to 4 different dropping downs or 4 different changes of these electrons from one state down to a lower state, and it's releasing those energies. So we have this idea, and we often write these little diagrams like what I've written over here, where we've got a lower state, call it E1, energy 1, a higher energy state, E2, and if you give the atom energy, it can take that and promote that electron up to a higher energy stationary state. Right? Or if it's up high and it drops down to a lower one, it can release that energy, and it could do so in the form of light or some type of energy being released, but we're talking about light here in this case. And so I could talk about the difference of the energy, E2 minus E1. Right? I don't really care so much what exactly E1 and E2 equal, but I do care very much about the difference between them. So whether it goes from 10 down to 15, 10 down to, say, 5, which is a split of 15, or a split of 5 is what I'm thinking, or whether it goes from 20 down to 15, which is also a split of 5, that doesn't matter so much as the change. The change in the energy is going to be carried away by these photons. Right. The energy levels, here's the third part of the Bohr model, the energy levels of these states, so E1, E2, E3, is given by this equation right here, negative k over n squared. This looks remarkably similar to the idea that Rydberg and Balmer had, right? Where you had the 1 over n squared in that equation, and that the energies scale as the negative 2 power of some quantum number, some numbering of the energy states. All right. Anyway, well, he was looking at of course, the Balmer series and the Rydberg when he's thinking about this. And so negative k over n squared is proportional to it, where again, n is going to equal 1, 2, 3, etc., etc. Okay. Why this negative, by the way? Does he want negative energies? Yeah, actually he did, and that's the way we're still thinking about that, because again, the exact energy level doesn't matter so much as the change in the energy. So why negative? What's up with that? Here's the idea. If you got a neutron, or nucleus, I said, where the neutrons and the protons are, if you got a nucleus and then you got some electron out here, okay, where would we want the energy of this to be 0? We want it to be 0 when it's close, when it's far away. What gives here? Well, the idea is we want it to be 0 when it is no interaction, right? When they are so far away from each other that they don't even see each other. We're going to call that 0. They don't interact at all. Then as they get closer and closer and closer, right, then we have lower and lower and lower potential energy. Just like if you have the ground and you got a ball that's being thrown up or down, whatever, the higher that thing is, the more potential energy it's got in that gravitational field. And they're being attracted to each other, and as it gets right down and finally sits on the ground, right, there's no potential energy. As you go up higher and higher, then you got more and more potential. We wanted the same idea. If you got a nucleus, you've got an electron, as you go higher and higher or farther and farther away, you want that to be a higher and higher potential. But we already said that way, way out there, we'd have 0. We don't have any interaction. So actually the highest potential energy in this kind of a description is 0, when it's just not interacting at all. And then as you get closer and closer, you get smaller and smaller. Of course, if you get smaller than 0, that means you're down in the negative numbers. So yeah, we actually have negative energy levels. A little strange at first to think about it that way, but again, we could scale that however we want to. I mean, think of temperature. Temperature on the Kelvin scale starts at 0 and it goes up and it's always positive. But I could do the same thing on the Celsius scale, where I can both have positive and negative, because 0 is where water freezes. And so whether it's positive or negative, that's just a scaling sort of a factor. It's a relative sliding, and don't let that bother you too much. So we do have a negative k, some constant, over n squared. Okay, and so the difference in that, you can say the final minus the initial, and again we have this subtraction of these 1 over n squareds, just like we saw with the Balmer and the Rydberg constant, the change of it. Right? So again, now he's talking about the electrons themselves, the energies, the potential energies that the electrons themselves in an atom would have. And he says, hey, they're ranked on these energy levels, and the difference between them, therefore, is going to be given by this equation right here. Okay. Of course, if when you fall from a higher energy level down to a lower energy level in this atom, you're going to release that energy. It's going to be going off perhaps as a photon of light. We already know the equation for the photon of light. Max Planck told us that. He said that, hey, the energy of a photon of light is h times nu, right there. Okay, well, if the change in energy, the amount that gets released from this atom, according to Bohr, is that much, and it's being taken away by a photon whose energy is that, we can set those equal to each other. Or if you want, plug in c over lambda instead of nu. We talked about that before. Then you would get, and then solve it for 1 over lambda, you would get this equation. 1 over lambda is this constant that Bohr used over hc times 1 over n squared minus 1 over n squared. Hey, doesn't that look very, very, very similar now to the Rydberg constant, where k over hc is equal to what Rydberg figured out, RH. Right? So yeah, RH equals k over hc. We know h, that's Planck's constant, and c is the speed of light. It's kind of cool how all of these start interacting, and all of these start being related to each other. Right? And so the Bohr model, if you make those electrons stay in stationary states with certain energy levels, and those energy levels are described by quantum numbers of n, 1, 2, 3, 4, right? And you assign them the energy of negative k over n squared. That model for hydrogen simplifies or predicts exactly the same thing that we saw with Rydberg. Right. What does k equal? Well, we know what k is that. We know the Rydberg constant. Didn't we talk about the Rydberg constant already? Yeah, we did. And so plugging that in, you get what k is, 2.179 times 10 to the minus 18 joules. Right? So k, again, from the Bohr model, and it's related to the Rydberg constant itself. Now, before we said that this works for hydrogen or hydrogen-like atoms. Now, what are we talking about there? Well, hydrogen has 1 proton and 1 electron. Right? And so if you have, and we're talking about the energy levels of these electrons, right? We're not really thinking about the nucleus at all yet, other than that it's positively charged perhaps, or something like that. And so hydrogen-like atoms would be other atoms with only 1 electron as well. For example, helium. Helium normally has 2 electrons floating around. If I make it a helium plus 1 by removing one of those electrons, now it's hydrogen-like. Yeah, it's got a bigger nucleus, more charge in the nucleus, but it only has 1 electron. Or I go up to lithium. Lithium would be plus 2, because it usually has 3 electrons, right? Take 2 of them away. Now it's hydrogen-like, that ion. And so there's not a whole lot of them out there, but helium plus 1, lithium plus 2, beryllium plus 3, those are all hydrogen-like. How does that affect this? Would they obey it? Hey, it turns out that they do. That those ions do obey the same sort of a Rydberg, Bohr sort of a model, as long as you also include the charge of the nucleus. And all we had to do is take those energy levels that the Bohr model used, instead of just letting it be a negative k on the top of the fraction, multiply that also by z squared, where z is the charge. For hydrogen, it was just a 1, so 1 squared is 1. It was still there, it's just we didn't see it. But you go up to helium, where the nucleus has a plus 2 charge, now it's going to be 2 squared, or a 4 is up there. Okay? And so whatever the charge of this hydrogen-like nucleus is, you just plug that in squared on the top. All right. And so this is the Bohr model. Just the idea that the electrons are in steady states with assigned energy levels. All right? And it fits very nicely the data that we see from the line spectrum. This energy scaling, if you will, this energy levels, the nth energy level would equal negative k z squared over n squared. What does that actually look like if we spread them out and showed them? And that's what the book does in this figure here. Increase in energy going up, and so here n is 1, n is 2, 3, 4, 5, right? And so we're going higher and higher in the actual energy. And remember, they're all negatives, but that's okay. Negative 2.18 times negative 18, negative 5. Notice they're getting smaller and smaller and smaller as we go up. What if we went up to n equals 100 or 1,000? Eventually they're going to hit 0. Remember, we said that the very top was 0. That's the maximum energy we have. And so on this sort of a diagram, I'll get my pen here. On this sort of a diagram, as it goes up and up and up, some maximum would finally be reached right here, where energy equals 0. And as we go higher and higher and higher, they start clumping and clustering and getting close together. When you go down to n equals 1, the very, very bottom one that you can go to, see it's fairly widely spaced from 1 to 2. And then from 2 to 3, not so spaced, and then from 3 to 4, and it just gets closer and closer and closer until, oh, I just realized they already have this. I'm going to go ahead and erase my little scribbles because they have it already. Look at that. Right there. When you get up to infinity for n, then you get 0 energy, and that's this very top line right here. It would finally just kind of cluster all together. But they're very spread out when you're talking about these lower energy levels right there. All right. Why does it cluster, by the way? Well, if the energy level equals, scroll back up here, some constant essentially divided by n squared, you're dividing by larger and larger and larger numbers, and so yeah, eventually it's going to go to 0. Just take the limit of this as n goes to infinity, you'd get 0. Alright, what's interesting about this is it also predicts the distance of that electron from the nucleus. Now see, we know if you got a positive thing and a negative, they're going to be attracted to each other. That's called a Coulombic attraction due to charges. And it's positive nucleus, negative electron, yeah, they're going to be charged. But that's going to be dependent, how much attraction they feel is going to be dependent on how far apart they are. Again, if you take them all the way apart, they're not even going to see each other, and you have 0 attraction. Right? But if you get them very close and closer, they're going to feel stronger and a stronger and a stronger attraction. Right? Same thing happens in a gravitational field. Right? The closer they are, the more strongly they'll be attracted to each other. And so we can calculate actually, well, how far apart are they? You know, what is the distance? Right? And in this sort of model, we've got this potential energy of the electron, which is governed by what stationary state it's in. That would also give us the sense then of, well, the ones with the highest energy, they must be the farthest apart. They're going to feel the least attraction, but they're going to have the highest potential energy. And then the ones that are closer, again, has the lowest energy, the lowest negative number, that is to say, but they're going to feel the strongest attraction. And so looking at the magnitude of the attraction, we get a sense of the radius. The radius r, which is the distance. They call it r for radius, I suppose, because if you think about this in a circular sort of an anti-atom, we're talking about the radius of how far that electron is from the nucleus. That equals n squared over z times a naught, where a naught is called the Bohr radius. The Bohr radius is just kind of like the calculated average distance of that electron in the lowest energy state. And it turns out to be 5.292 times 10 to the minus 11 meters. Alright, so that's just a constant, just like c and the speed of light, that kind of thing. H, Planck's constant. Alright, this is the Bohr radius constant. That's how far, on average, the electron in the lowest energy state would be, according to the Bohr model. Right? And so if you think about this, again, as the energy increases, so does the distance of that electron from the nucleus. In exactly the same way, again, that a rock has more and more potential energy as I increase its distance from the ground. Boom, and it falls back down. Okay, so it's easy to remember. Example 6.4. It says, let's see, researchers were very excited to be able to predict the energy levels, hydrogen atom. If a spark promotes an electron in a hydrogen atom up to n equals 3. So it was starting at either 2 or down at 1, not sure, but you sent some electricity through it and made it up to 3. Let's calculate the energy of that electron. So now that it's sitting up in the n equals 3 level, we've got, of course, the energy level is negative k z squared over n squared, where K is, as usual, 2.179 times 10 to the minus 18 joules. Z, this is a hydrogen, so Z is just a 1, so 1 squared, and divided by 3 squared, n squared, right? N equals 3 for this case. All right, and so now we just plug that into the calculator. Sorry, my cord was getting caught in something. All right, negative 2.179 E minus 18. And divide that by 3 squared, which is a 9. Our result is negative 242 times 10 to the minus 21 joules. Or if you prefer, that would be negative 2.42 times 10 to the minus 19 joules, right? If I just take that and move it over 2 places. All right, so there you go. There's my answer. That's how much energy it's got when it went up to the 3 level. All right, now the Bohr model. If we take this and apply it to this idea of the line spectrum that Balmer and Rydberg were thinking about. I've already talked about this connection before. Here is a diagram from the book laying it all out. Here we've got the energy levels of the hydrogen atom. The lowest energy level, which is also called ground state, because it's like the ground, right? It's the lowest one you can go to. Down here, n equals 1. Next one up, n equals 2, 3, 4. And you see how they're starting to cluster as I get higher. And if I promote that energy to a higher level by shooting some electricity through it, or maybe if it's at a higher level and it falls back down, releasing a photon, the difference, if I subtract those energy levels, right, the difference would tell me the energy required to either bring it up or the energy that the photon carries away with it. So I can talk about different transitions. If I transition it from here, say a 1 up to a 2, the final is a 2, n equals 2, the initial was n equals 1, and I could use the Bohr model and the energy levels to calculate what the change in energy is. That is to say, how much energy did I need to make that promotion. So here, on this line here, this would be a 1 up to an infinity. This would be if I give it enough energy that the electron goes so far out that it is ejected. That is to say, it's no longer even part of that atom. Okay. But if I don't go quite that far, like say I take this middle line here from 1 up to this yellowish one, which is a 4, so that would be a difference from 1 up to 4. Or here's a 2 up to a 3, or a 2 up to a 5, or those type of ideas. All right. Interestingly enough, you see the size, again, of these energy splits is the energy of the photons. And if you go down to the 1 level, that next level up is so far up, that's a large amount of energy required to promote it up. Or if you've got one of these in these upper levels falling all the way down back to the 1 state, those are very large amounts of energy. And if it released those large amounts of energy as a photon, that'd be a very high energy photon, like in the ultraviolet, way up there where it's really high energy, beyond what our eyeballs can see. If, on the other hand, we're talking about different splits of energy, say from the n equals 2 up to a higher one, right? From n 2 to 3 or 2 to 4 or 2 to 5, these guys right here, or the reverse of it, say they're already up here and they fall back down to the 2 level, those are much shorter lines, right? Smaller amounts of energy. And it turns out that that smaller amount of energy is the same as the energy that our eyes can see. That is to say, in the visible spectrum. We can see those with our own eyeballs. And when Balmer was looking at the hydrogen, he shot that electricity through it and saw those lines coming off. What he was actually seeing was these guys. Something from, say, a 2 falling down to, a 3 falling down to a 2. That was the shortest of the arrow, or the smallest energy is what I'm trying to say. The smallest energy photon that was released. And you remember those 4 lines? Here they are. I copied it down here. The small lines, they've got the red and the blue and the ultraviolet. Remember, ultraviolet, those are the high energies. As you go to the red side, that's the low energy. And so that very first line here on the right, from the 3 down to a 2, would correspond to this photon right here, the red one, the one with the lowest energy. The next one up was a 4 down to a 2. Hey, that's this blue line here. 5 down to a 2, that's this purplish line. They're not shown in this diagram, but if I went from a 6 down to a 2, that would be this purple line right here. As I fall from a higher one that's releasing more energy, it's a longer arrow, which means a higher energy, and therefore I got to go to the frequencies with higher energy. Remember, energy scales as frequency, and so the ultraviolets have the higher energy. There's your 4 lines then. It corresponds to these 4 transitions from a higher energy down to the number 2 level. So when we shot the electricity through the hydrogen, the electrons on those hydrogen atoms were excited up to these upper levels, and they started falling back down, releasing photons. Hey, did these transitions occur? Yeah, they were also occurring, but our eyes can't see them. They're in that part of the region beyond what we're sensitive to. So they were sure occurring, but we can't see it. But these guys were also occurring. Some of them just stopped at 2. They didn't go all the way down, and we were able to actually see those transitions. All right, very, very important to understand all of that. All right, the Bohr model, therefore. Nice model to explain these line transitions of hydrogen, or hydrogen-like. However, it does not account for unhydrogen-like, or in other words, atoms that have more than just 1 electron. See, if you got 2 electrons that are whizzing out there, and each of them perhaps a stationary state with different energies, but these electrons, both negative, they're going to interact with each other. They're going to want to repel each other. All right? And say you get something up like lithium where you have 3 electrons, or you go farther, beryllium with 4 electrons, etc. As you get these additional electrons, they're going to be interacting with each other, and that's going to change that whole energetic scheme. It won't be as simple as it is for hydrogen. So, the Bohr model does not account for anything that complex, but it does account for anything that's hydrogen-like, that is to say with 1 electron. All right? The Bohr model also, and I've listed it here, does very importantly these things. Number 1, it has this idea that the electrons have quantized energies and distances. So again, this idea that these steady states and they have very particular energies. Their energies are quantized. They can't go anywhere in between it. They have to be in one of these steady states that correspond to one of these particular energies. Okay? And again, different energy electrons would correspond to different distances. And so more or less, at least as far as the Bohr model can be interpreted, as I go to higher energy electrons, I'm talking about electrons that are being held further and further away from that nucleus. Right? As the energy increases, I get towards the highest, and remember the very, very highest would be an energy of 0, which is I've totally ejected it from that atom. The electron is free. Okay. So the idea of quantized energies and distances. Number 2, quantum numbers. Those n's, n equals 1, 2, 3. Right? The idea of a quantum number is being able to address or index, if you will, these different energy states. Very important. That shows up in the Bohr model. Number 3, the distance goes up, so does the energy. Just talked about that. And I always relate that back to, again, the rock or the ball being held above the ground. The higher you go with that, the higher the energy, but the potential energy of it. Same thing with these electrons. The further that distance is from the nucleus, the higher the energy they are. And again, the highest could be 0 when you totally removed it. And finally, number 4, the line spectra is great evidence for this quantization, because again, we got the transition from a higher level down to a lower level, releasing that amount of energy, whatever that split is, and that energy gets taken away as a photon that we can see if the photon has the energy that our eyes are actually sensitive to. Example 6.5 says, what is the energy and the wavelength of the line spectrum of hydrogen that represents from a 4 up to a 6? So we got a hydrogen atom, it's at 4, we're going up to 6, it's going to need some energy, and if we give that in the form of a photon, it's asking what is the wavelength and the energy of that photon. And then finally, what part of the electromagnetic spectrum do we find it? So, is it in the IR, the UV, the visible, the X-ray? What portion is it in? All right, so we've got some initial 4, a final 6 level, and again, we're trying to find out what part of that spectrum it is. Well, we know that the energy levels of a electron is equal to, sorry about that, is equal to negative k z squared over n squared always, and therefore the change in energy is always equal to negative k z squared 1 over n final minus 1 over n initial. And we know everything. We know what k is. We know z is 1 because it's hydrogen, and the initial is 4 and the final is 6. So we can plug all that in. Delta E is equal to negative 2.179 times 10 to the minus 18. That's k. Z squared is just 1s. And then we have 1 over 6 squared minus 1 over 4 squared. Alright, so let's go ahead and plug that in on the calculator. Negative 2.179 e minus 18 times, in parentheses, 1 over 6 squared, that's 1 over 36, and 1 over 4 squared, that's 1 over 16, equals. Okay, so the change in energy is positive, 75.7 times 10 to the minus 21 joules. Or if you prefer, that be 7.57 times 10 to the minus 20 joules. So there's the energy of the photon that's being released. If we want to calculate its wavelength, we know that the energy of a photon is also equal to h nu, or hc over lambda, and that's what we're trying to find is lambda, so we'll go ahead and use that one. 7.57 times 10 to the minus 20 would equal h, which is 6.626 times 10 to the minus 34 joule seconds. C, 2.998 times 10 to the 8th meters per second, and all divided by lambda. Of course, joules and joules will cancel, seconds and seconds will cancel, and lambda will come out in terms of meters. So again, we'll go over the calculator and punch that through. We've got 6.626 e minus 34 times C, 2.998 E8, divided by the energy, 7.57 E minus 20. All right, lambda is 2.62 times 10 to the minus 6 over here. And again, that's meters. Well, that's definitely not in the visible. The visible is up there at the -9, about 400 to 700 nano. And so if we scroll all the way back to the beginning of the chapter here, where it's talking about, there we go, the full range, 10 to the -6 region, we're in the here. So that looks like it's in the infrared. And so we're not going to be able to see that. It's in the infrared portion. Did I look at that right? Just double check that. Oh yeah, here we go. Yeah, 10 to the -6 down here in the infrared. So that's what I would say. This is an infrared actual photon, infrared portion of the spectrum.